Hi, in this short video I will discuss the SIR rate equation model for the spread of virus infection. I will use this model and apply it to the coronavirus outbreak from 2020. The main idea of the model is to divide the entire population in three groups: the susceptible people, the infected people, and the recovered people. The idea is to take one person, for example, in the susceptible, and move it towards an infected category, and then take a few infected people and move them to the recovered. And so in general, you can only have susceptible people which get infected and then eventually recover and become recovered people. So that's really the basis of this SIR model, and as you probably realized, the name just comes from the susceptible, infected, and recovered population distribution. An important assumption of this model, I will describe this in the context of some slides adapted from Anne Bochel, and where I repeat the main assumptions. One, that the total population is fixed, will not change, and that it's divided in these three categories: S, I, and R. So the question now is, how do I model this mathematically? Well, I have this bin, S bin, which is the number of susceptible people, and the first step is just to look at how do people which are susceptible to the infected become infected. I describe this by the change in number of susceptible people, and that's simply the derivative in time of S, and it's equal to the number of people who get infected. This number of people who get infected is proportional to the transmission coefficient, the number of susceptible people to get infected, and also proportional to the number of infected people. So what happens is that if I start at some time t-1, I take out the number who get infected, which is minus beta S times I get the number of susceptible people reduced by this amount, and that's the new number. Now, these infected people, minus beta S, they transfer to the bin of infected people, and so they increase the size of the infected people by exactly the same amount which we take away from the susceptible bin. Now the next step is to look at what happens between the infected people and the recovered people. So here I also have a certain number of infected people which will recover, and they transfer into the recovered bin. And again, note that the sum of the two is again 0. So the total population between susceptible, infected, plus recovered is always going to be remaining the same. So I'm not changing the total population. And then finally, and another important quantity is the death rate. And so that's the number of people who die per day. And that's going to be given by some rate, m, and that's m is a coefficient which is going to be smaller than 1, and multiplied by how many people are recovering. And so some of these recovered people are basically going to be dead, because they're not going to be susceptible anymore to get infected. And so they're essentially removed from the mass of people who could be infected. So let's look at applying this model to some example, and I'm going to take some number of some size of the target population, n equals 120,000. I'm going to define some transmission probability as being alpha equals 0.018, some contact rate, and the contact rate is simply how many contacts an infected person has per day with susceptible people. So that's, which means that the transmission coefficient, so the probability to infect new people, is given by beta, and it's equal to alpha c divided by n. So it's proportional to the transmission probability and the contact rate, and divided by the total population. And it's also going to depend on the infection duration. And then I also introduce the mortality rate, and I assume here it's 3.5%. And then there's another important number, which is the reproduction rate, R, which is equal to alpha C times D. And to better understand why that is, I'm going to go back to the previous slide, where I'm going to look at this di over dt. So let's take the first case, where di over dt is positive. In this case, that means that the number of infected people is going to increase over time. However, if di over dt equals 0, that means that the number of affected people is remaining constant, will not change over time. So if I take this into that equation, I see that in order for di over dt to be equal to 0, I need this beta s times I equal to I divided by d. On both sides I have I, so I can cancel this out, and what I'm left over with is beta s times d equals to 1. Now we saw in the previous slide that beta is basically just alpha c divided by n, and at the beginning of the outbreak the number of susceptible people is roughly equal to the total number of people, so this cancels out again, and so what I have remaining is basically alpha c times d equals 1, and this variable here is what I call r. And so we see that if r equals to 1, then that implies that the derivative of di over dt is 0, and so that the spread is not changing. So the number of effective people does not change over time. However, if r is bigger than 1, then di over dt is bigger than 0, which means that the number of infection increases, while if this number is smaller than 1, then we have basically contained the spread of the disease, because di over dt is going to be smaller than 0. Okay, so now let's go back to the numbers. So we understood what this reproduction rate is, R, and we're going to assume in this model that it's going to be equal to 3.3. And now I'm going to look at what is the consequence of these numbers on the solution of the model. To solve this model, I simply used an iterative equation and a simple Matlab program to solve it. And the solution of that model is are the blue dots. So this is the result of the simulation. And then I also have the blue crosses. The blue crosses are basically the number of deaths per day, while the blue dots are the number of infections, daily infections. And the red curve is basically the data from the Chinese coronavirus outbreak. And we see that the data and the model actually works quite well, and reproduces, the model really reproduces all the features we see in the data. So we have sort of a maximum in this case, which is about 10,000 new infections per day, and we also have something like 200 maximum of daily deaths per day in the peak of the outbreak, which is roughly 40 days after January 1st. We can also apply the same model to South Korea. In the case of South Korea, the main difference is that we have to assume that the target population is much smaller, 10,000 instead of 100,000. And then we also have to assume that the mortality rate is slightly smaller, but all other coefficients are the same. So I still keep 3.3, 8 days, 23 contacts per day, and a transmission probability of 0.018. In this case, what we see is that the maximum number of new infections is limited to about 1,000 per day, while the number of deaths per day is not exceeding 10 cases. And so, to summarize, we have introduced this simple SIR model, looked at how it fits the data of the coronavirus outbreak of 2020, and see that it really works quite well. And so with this, I would like to thank you for listening, and I hope you enjoyed this video. Thank you.